Given an integer array nums and an integer k, choose exactly k distinct non-empty subarrays. They may overlap but the same indices cannot be picked twice. Each subarray scores max minus min inside that range. Goal: maximize the sum of all k scores. First pick indices 0 through 1. Max is 3, min is 1, so the value is 2. Second pick indices 0 through 2. Max is still 3 and min is still 1, value 2 again. 2 plus 2 gives output 4. Example 2. Nums is 4, 2, 5, 1 with k equals 3. First pick indices 0 through 3. Max 5, min 1, value 4. Second pick indices 1 through 3. Max 5, min 1, value 4 again. If we try to tackle this problem by checking every single possible subarray combination, we quickly run into a wall. For a massive array, a nested loop checking every left and right boundary creates an O of n squared coordinate lockout that is far too slow. To unlock the optimal pipeline, we need to completely avoid brute force scanning. As a quick refresher, remember that a sparse table is a static grid built specifically for answering range queries. Instead of storing every possible window size, it pre-calculates answers only for windows whose lengths are exact powers of 2, like 1, 2, and 4. Because of this structural design, any arbitrary query can be answered in absolute constant O of 1 time by simply looking up and overlapping exactly 2 pre-calculated blocks. Let's uncover the core mathematical rule that makes an optimal solution possible. If we lock down a fixed starting position L and begin shrinking our window by pulling the right boundary R backward to the left, the range of elements narrows. Because the window is shrinking, the difference between the maximum and minimum elements inside can only stay the same or decrease. It can never increase. This structural property gives us an immediate shortcut. For any starting index L, the absolute maximum score it can ever possibly generate across the entire problem is its widest possible window, stretching all the way to the very end of the array. By looking at these 4 primary boundaries, we instantly isolate the highest scoring candidate for every single starting position before we ever waste time checking the intermediate windows. Instead of manually calculating every single subarray combination, we query our pre-built max and min sparse tables. For each of our 4 starting positions, we instantly pull the maximum and minimum values for their widest possible windows. Because sparse tables guarantee constant time lookups, we compute the definitive peak scores for all 4 starting tracks simultaneously in O of 1 time. We package these starting boundaries and their scores into individual data packets and drop them straight into a max heap. The heap immediately handles the organizational logistics. It automatically sorts the packets, instantly pushing our 3 highest scoring candidates directly to the front of the line so they are ready to be harvested first. But what happens to the remaining, smaller windows? This is where our heap gets incredibly efficient. We don't load them all at once. When we evaluate a top packet covering the range, L, R, it acts as a gateway. Only when this packet is used do we dynamically generate its next best alternative, the slightly smaller window, L, R, 1, and push it back into the heap to be sorted. Finally, we run our extraction loop exactly k times, which in this case is 3. We pop the heaviest packet waiting at the front of our max heap, add its score straight to our running total, and immediately push its next best shrunk variation back into the heap. Because our sparse tables guarantee O of 1 lookups and our monotonic property ensures we only step downward from maximum values, we successfully harvest the top 3 global scores in optimal time while leaving the vast majority of lower scoring combinations completely untouched. Our implementation begins by initializing 2 independent sparse tables, one for range maximums and one for range minimums. To keep our focus squarely on the core algorithm pipeline, we are skipping the internal loops used to construct the tables here. This pre-computation step runs behind the scenes, giving us an instant, constant time gateway to evaluate any subarray value later on. To clean up our main loop, we define a small helper function. It accepts a left and right boundary, queries both the max and min tables simultaneously, and returns the net score. Because it relies entirely on our pre-computed tables, this helper executes in true constant time. Next, we allocate our priority queue. We loop through every possible starting index L, calculate the value of its widest available window stretching all the way to the end of the array, and push it into the heap. The max heap architecture ensures that the largest actual scores always bubble up to the very top of our sorting queue. With our peak options loaded, we launch our extraction loop exactly k times. In each iteration, we pop the highest scoring element off the top of the heap and add its score directly to our running total. Then, if the window has room to shrink, we calculate the score for the next narrower interval, from L to our -1, and push that alternative configuration right back into the heap. Once the loop has completed all k extractions, the remaining items are left untouched in the queue, and we return the finalized accumulated total score. Let n be the length of nums and k the number of subarrays to choose. Time is O of n log n plus k log n, building the twin sparse tables costs n log n, seeding n widest windows adds n log n heap work, and k lazy extractions cost k log n. Space is O of n log n for the two sparse tables, which dominate the priority queue. Function max total value, given nums and k, return the maximum total subarray value. Assume a max sparse table is already available, we skip that build here. Same for the min sparse table, details are omitted. Create an empty max priority queue. Let n be the length of nums. Loop over every possible left boundary L. Call getValue on the widest window, details omitted. Push that score with its left and right indices into the queue. Initialize the running total score to 0. Repeat exactly k extraction steps. Pop the highest scoring tuple from the queue. Add its score to the running total. If R is still greater than L, the window can shrink. Call getValue on the narrower interval, again, details omitted. Push that alternative back into the queue. Return the accumulated total score.